It's now time to restart our session. The next speaker is Professor Shota Sakamoto from Tokyo Institute of Technology. And the title of his talk is The Well-Posedness of the Boltzmann Equation Without Angular Cutoff in Some Banach-algebra Spaces. So please.
Thank you for your introduction, and thank you very much for the organizers for giving me a kind invitation to this workshop. My research interest is in the kinetic theory, especially the Cauchy problem of the Boltzmann equation. So I am afraid if my talk is slightly out of the scope of the workshop. However, I wish if you could enjoy my talk. Good. So I first give a brief introduction to the kinetic theory and the Boltzmann equation. And then we want to consider a Cauchy problem of the Boltzmann equation. So I will set the problem in the second section. And after introducing some prior results, we will show some main theorems of my talk. And finally, as time permits, I will give some proof outlined. Okay, let's start. A dilute gas, the example is air in the outer space, which is away from the surface of the Earth about 80 kilometers away, consists of a vast number of particles which collide each other and move randomly. And it cannot be modeled as a continuum gas. The example is usual air in my office or in your office, in your home, everywhere, or the atmosphere of the Earth, because the densities of each gas are very different. I believe that the very fundamental hypothesis for continuum mechanics is that even though molecules in the air, like oxygen or hydrogen or nitrogen, etc., are discrete, but their density or their distance between two molecules are very small, so that we cannot, how to say, sense. So they can be regarded as a continuum, well, as its name says. And by that assumption or hypothesis, we can derive Navier-Stokes, Euler, or other kind of fluid equations. However, if you consider a dilute gas, the distance between two molecules are not so small, especially when compared to that in continuum gas. So we need a different modeling. Especially, we have to take into account the collision of particles or molecules. The study of such dilute gas in this principle is called the kinetic theory, and the Boltzmann equation is one of the most fundamental equations in the theory. This is the Cauchy problem of the Boltzmann equation. dtf plus v dot gradient f equals to QFF. I will define this operator Q later. And the second one is obviously initial data. Here, T means time, X is in the domain omega. We consider the case omega equals to either R3, the whole space, or T3, the torus, the three-dimensional torus. This represents the position of particles, and V is the velocity of particles. This can also take value in R3. And the capital F is the unknown function. Physically, this means that probability of observing a particle with velocity v with velocity v at position x and at instant t. And the dilute gas is governed by two effects. One is transport part, the left-hand side, because as you can see, dt and v dot gradient x means that if there is one particle, and if velocity v, for example, this direction is given, then it moves alongside that direction. And that's only it. So this is transport part. And the QFF takes into the account of collisions. I will define this later. So governed by two effects, transport and collisions, the system evolves, and we want to find a solution, capital F. Before looking into Q in detail, we have to see the collision rule. So yeah, there is another picture here. I don't know the reason why, but I couldn't convert this to a PDF file. But anyway, assume we have two particles about to collide with velocity v and with velocity v star. They are about to collide here, and after the collision, we get other velocities, v prime and v star prime. So when we look into these relative velocities, v minus v star and v prime minus v star prime, we can find that, I'm going back to the original PDF. We can find that by conservation laws of the momentum and energy, the four vectors, v star, v prime, and v star prime, they should be on the same circle because they share the same, the relative velocity. This one and this one share the same middle point, and they are the same length. So they're on the same circle. This is a rule. And for later use, I will define unit vector sigma for this direction. Once this direction is given, post-collisional direction is governed because the other one goes completely opposite side. And for here, deviation angle is called theta. Now, the collision operator Q is defined by this integral. Looks messy, but this capital B is kind of a weight function stating that what kind of collision likely to occur or not. So if capital B is large, then collision given by this V star and V sigma are likely to occur. And this, how to say, difference part here says the probability or a probability of gaining or losing velocity v. Oops, maybe I should have said that this collision operator makes another kind of probability density from two densities f. And we can put this g, but for simplicity, I put two f's here. Here we have v star prime, sorry, f of v star prime and f of v prime. This says that since f is a probability of observing a fixed velocity, and by classical mechanics, we can know that if this kind of collision happens, then the opposite one, I mean, or reversible one, like this, sorry, like this, should also happen because the collision is reversible. So if the particles with velocity v prime and v star prime collide, then we should gain velocity v. And this is the reason why we have a plus sign here. From this part, we gain velocity v. And from this part, by the opposite reason, we have minus, because if two particles with velocity v and v star collide, we get v prime and v star prime, but we lose velocity v. So here we take into account the collisions of losing velocity v. And if we consider all the possible collisions for fixed v, then we should take integral. So by taking the integral, we can say that we can consider all the possible collisions. And this is the meaning of the collision operator. And this explicit identity for v prime and v star prime as a function of v star and sigma is, you can show equivalent to these conservation laws. Since this is not, this is implicit for v prime and v star prime, we would rather stick to this equivalent formulation. And physically speaking, the most important example of B, capital B, weight function, is this. This is a product of two parts. The one is a function of theta by cosine theta, and the other is the magnitude of relative velocity v minus v star to some exponent gamma. And gamma takes value in this region. Well, there is a physical reason about this, but sorry, I have no time to explain about that. So allow me to do that. And so gamma, when gamma is negative, we may have singularity on this set, v equals to v star, and b cosine theta also has singularity, this one. Especially b cosine theta is not integrable on S2, because from this part you may get 1 sine theta, but that's not enough, because even though we have 1 sine theta, we still have theta to -1 minus 2s, and this is not integrable in theta. And this assumption is called the non-cutoff assumption, assuming the non-integrability of b cosine theta. And in the mostly 60s to 80s, I guess, it used to be assumed that the b, small b, is integrable by cutting off the singularity. So it's called the cutoff assumption. This makes problem easier because we can naturally divide the collision operator into two terms, because here we have minus sign, so we may divide them into two parts, and one is coming from this part and the other coming from this part. So it's easy. Well, I mean, relatively easy. And we can analyze them separately. However, the singularity arises from the derivation of the Boltzmann equation. So it's natural to assume the non-cutoff assumption, and that's the reason why the non-cutoff assumption is important, how to say, research topic. Even though I am not going to in this topic in detail, but I want to emphasize on one thing, on one difference between the cutoff and the non-cutoff cases. Practically speaking, a solution to the cutoff case describes the real phenomenon rather well. Actually, this was observed by there are two fathers of the kinetic theory. One is, of course, Boltzmann, and the other is James Clerk Maxwell. And Maxwell himself observed by theory and experiments, I guess, that cutoff model describes the real phenomena rather well. And in view of solving PDEs, many important properties like existence and uniqueness of a solution, convergence to an equilibrium of a solution, and its decay rate, they are the same most of the time. But there is one big difference. Locally speaking, well, maybe I should say linearized cutoff equation is hyperbolic. I don't define this capital A, V, but this is some kind of multiplication function. So you can use the method of characteristics and easily find that the solution small f cannot be smoother than original initial data if zero. However, the non-cutoff case, the linearized equation locally described by this equation. This is called Kolmogorov type equation. And here we have this fractional Laplacian. And this S, this 2S, coming from this one, this singularity. So this is the reason why non-cutoff assumption is important. Okay. So if we do not assume the singularity, we cannot gain this fractional Laplacian. And even though this fractional Laplacian works for V variable, thanks to this term, there happens some kind of mixing in variables. So we can get not only V smoothness, but also X smoothness we can get. So smoothing effect of the equation is a big problem. And I wish to address this problem near future, but today we are not going into. Right, let's go to a setting of a problem. What we actually consider today is a perturbation problem, and it is known that this function is an equilibrium. I don't show the proof today, but it's not so difficult to show that this is an equilibrium, and this is called Maxwellian. So that's the reason why we use M. And if we plug this capital F equals to M plus some perturbation for small f into the original equation BE, then it is recast as follows. This is PBE. We had dt plus v dot gradient x, so there are no problem. And we had capital Q, the collision term, but it's not now decomposed into two parts. The one is a linear part, and the other is, of course, a linear part. And of course, we have initial data if zero. And we will discuss the well-posedness of this perturbation of Boltzmann equation PBE in various spaces. This is technical remark, but we restrict ourselves to the so-called hard potential case. Gamma plus 2s is bigger than or equals to 0. This case is a slightly easier case, but we can, by our method, we can also treat this case where gamma plus 2s is negative, but not its modulus is not too large. For this soft potential case, we need some weight function, which makes statement of the theorem messier. So allow me to avoid that. Before going into prior result, the introduction of prior result, we have to remind some function spaces. I believe some of you, or maybe most of you, are familiar with these spaces, but allow me to remind once again. First, HS for S real is L2 based Sobolev space. Probably we do not need an explanation about this. And B3/2 is the inhomogeneous Bezel space. The definition is we employ inhomogeneous little Pauli decomposition. If you are not familiar with this, please think this as some kind of cutoff on the Fourier side. And the definition of the Bezel space is we first apply this cutoff or decomposition on the Fourier side and take L2 norm, and this 2 corresponds to this 2, and take summation with this weight 2 to something. And in the something, we can see there's a 3/2, which corresponds to here, and the last index 1 corresponds to that we are taking a small L1 norm, a small L1 sequence norm. And the next one is, well, it's not a definition, rather abbreviation. If I write a function space like this, then it should mean, for example, there is a function of t, v, and x, and we take first H2 norm with respect to x first, then take L2 norm with respect to v, then finally take L infinity norm with respect to t. I believe this kind of abbreviation is common. Next is the Sheman-Lerner type space. This is slightly different from the non-tilde space. If there is no tilde, then it should mean we first take Bezoff norm with respect to x, then take L2 norm with respect to v, and finally take L infinity norm with respect to t. However, if there are some tilde, the order of taking summation and taking LP norms are different, because here we first apply the little Pauli decomposition, the cutoff on the Fourier side, or decomposition on the Fourier side, then take all the norms first before taking summation, and then take summation. So all are different. So it can define a different topology. And the Wiener space for the torus case. Definition of this space is not so difficult because it says Fourier coefficient is absolutely summable. So I believe it's not difficult. And this can be, we can think analog for R3 case. That is, of course, f hat dk is finite. So I believe some of you or some of the people using the terminology Fourier-Lubeck space, if I'm correct, but I do not use that because just because I'm not familiar with it. And sometimes this space is denoted by L1k, and the k means the Fourier variable for x. So why do we have to use such kind of spaces? because they're useful for the estimate of nonlinear term, capital gamma. I defined in two previous slides, I think. And the key estimate for the nonlinear part is this. The norm of product Fg is bounded by some constant with multiplied with the norms of F and G. Here, Fg is in X, well, the element of X, and X is a Banach space. And if this X satisfies this condition, we say X is a Banach-algebra. I should remark that this definition or terminology is somehow loose one, because how to say, researchers of operator algebra says X is Banach-algebra when C, capital C, is exactly 1. But we allow here that C can be bigger than that. So it's loose definition. So what kind of space X satisfies this condition? The most fundamental example is obviously L infinity. I believe we do not need explanation about this. It's very obvious. And Sobolev space also satisfies this condition when for the L2 based Sobolev space, if this S is bigger than this one, 3/2, so dimension divided by 2. Because in that case, HS can be embedded into L infinity, and this kind of how to say, bilinear estimate always hold for the solved norm. So if we can bound L infinity norm with the Sobolev norm we are using, then we can have this estimate, the condition 1. Also, Bethoff space satisfies this condition, and the good point of using Bethoff space is S can be taken 3/2. S can be equal to 3/2, which wasn't possible for the Sobolev case. And in this case, BS can be also embedded into L infinity, so the condition 1 holds. And Wiener space also satisfies this, because the definition of the norm of Fg, product Fg, is that we take Fourier transform of Fg and take L1 on the Fourier side. But of course, the product can be converted to convolution. And by definition, or by using a Fubini theorem, this is bounded by the product of 2 norms. And by definition again, this can be written like this. So Wiener space satisfies condition 1 with a C exactly 1, like L infinity. Now, let me show you some known results. And these are L2 based results. L2X, I should say. There are some, how to say, other results based on using other L1 or L infinity base, but, well, I think L1 usually. So the first one is Go's paper, 2004. He showed, well, classical global existence in this space. So it's smooth in T and X because N is bigger than 4. So this is a sufficient smoothness for having a classical solution. But it was cut off. And later, Amixi and Grossman-Strang, well, Amixi is the abbreviation of Alexander Morimoto, Uka, Yan, and Shu, which is, I believe, common abbreviation for Boltzmann researchers, and they independently showed global weak solution, existence of a global weak solution in this same space, L1 infinity, H2x, L2v. But Amexi is for R3 and Grassmann-Strain is for T3. This was the first result establishing a weak solution to the non-cutoff equation near equilibrium. And Duan, Liu, and Xu established the global solution in this space, in this Schumann-Lerner type space. So if we look into this, how to say, Sobolev or differentiability index, we may say that this index is improved, but also this was for cutoff case. So Morimoto sensei and I, or how to say myself, improved this result for the non-cutoff case for the same solution space. These are, I should remark that these are used using L2-based Sobolev or Belov spaces, and as I said, the reason why we have to use this kind of space was to use this condition. So we may think if we can use other kind of solution spaces satisfying this condition 1. For example, if we can get a solution in L infinity x, it's very great, but it's too rough to construct a solution, and that's the reason why we started from the Wiener space. And this also has the this one condition 1 with C exactly 1, but it's smoother than L infinity. I will show you later. And the main theorems. The first one is a collaboration with Renjun Duan at the Chinese University of Hong Kong, Xuanzhang Liu at he moved to Normal Central China University, and me, S, and Strain at Robert Strain at Pennsylvania University. Suppose omega is T3, the torus case, and if initial data is small enough in this space, then the PBE, perturbation of the Boltzmann equation, has a unique global time solution in this space. X is for Wiener space. And we also showed exponential decay of a solution in the solution space. It has a different structure compared to L2-based Sobolev or Belov space, because this Wiener space AT3, for the three-dimensional case, this contains this C1 alpha space, Helder space. So it's more like L infinity rather than L2. And so it may slightly irregular, it may slightly too regular, however, we may, to our best knowledge, this was the first result to construct a solution of the non-cutoff Boltzmann equation or on the L infinity based space. Also, our proof can be applied to other cases, such as the Landau equation. And this is kind of brother of the Boltzmann equation, because let me go back much. Where is it? Oh, here I said gamma is coming from this part, weight function. I said gamma can't be taken -3, and in that case, we have to derive equation in a different way, and that's a Landau equation. However, they share many structural property of the equation, so we can use the same method to this Landau equation. And not only the torus case, but also initial boundary value condition, initial boundary value problem on this space can be also considered with the same, well, a little bit more complex, but in the same spirit. And this was also the, to our best knowledge, this was also the first trial, I believe. And the second theorem is due to Duan, the same Duan at Chinese University, me and Yoshihiro Ueda at Kobe University. Even though it's written in progress, but we have almost finished. What we are left to do is a final check. And suppose this case is for the whole space case. And we take index sigma 3 minus 2 epsilon, and the epsilon is arbitrarily small. And this will be used for decay rate. And if initial data is small in this space, so this is an interplay of L1k and L infinity k. So F0 is not only L1, but also L infinity on the Fourier side. Then we have a global solution, unique global solution, F. And this, sorry for the messy inequality, but this says this one and this one are energy parts, and this one, these two are dispersion terms. They are bounded by the initial data, well, the bigness of the initial data. And especially from this term, we can get time decay of a solution. It is known that for the three-dimensional case, decay rate of the Boltzmann equation should be heat-like, that is, in this space, minus 3/2. So it was great if we can take sigma equals to 3. However, we couldn't, but almost optimal decay rate. I will show the reason later. I will come back here if I have time later, allow me. And I believe I have 30 minutes left. So I will go into proof outlined, especially for the recent result, theorem 2. So we introduced the following triple norm. This can take into account the dispersion structure of the equation. This was defined by Amixi. I believe that this was defined before 2012, but this important inequality was shown in this JFA paper, so I wrote 2012 JFA. The definition of this triple norm is the sum of this. So I believe that if you are not familiar with the non-cutoff Boltzmann equation, probably this is not easy to see why we have to define a norm like this. But instead of explaining that, it can be very technical. So let me show you this estimate. So, oh, okay. Oh, sorry, I should say, instead of this triple 3 bars, I would like to use this capital D to emphasize that this is used for dispersion rate. And this FD has a lower bound, this one. It said that this is bigger than weighted L2 norm, where weight function is a polynomial with order gamma plus 2s. And for HS part, we have no weight function. So if we have a weight function only for 0th order term, then FD should be bigger. And if we employ a weight function for all the derivatives up to F order, then this FD is smaller. So this triple norm is invented to capture the subtle nature of between these two weighted functions or weighted function spaces. And so how do we use this triple norm? Amixi also invented a very useful lemmas. The one is capital P. Oops, I should have said that this capital P was in the theorem. Ah, yes. Here. And this P is orthogonal projection from L2 to null space of L, or zero eigenvalue part of capital L, the linear operator. And when we consider energy estimate, we have to have this kind of inner product, and this is bounded below by this. So from LF, we can get a partial dissipation because we lost the information of PF by these estimates. However, this can get information of I minus P part. So this is important. And we will recover the information of PF in a different way later. And for the estimate of nonlinear part, we use this by Amixi. It said that the inner product of H and gamma FG, well, we usually use this gamma FF, but it can be defined for general F and G. And the inner product of them can be bounded by this quantity. F is L2 V for F, and the dissipation norm for G and H. So it says gamma is not a symmetric operator, because if gamma is symmetric, then we should have L2F and G2F, or FD and GD, but not. So using these inequalities or lemmas, we can estimate the I minus P part with the energy part. This is the usual energy estimate, because where is the equation? As here. So if we multiply small f to this equation, then from this part we have the t derivative of norm of the f squared. And since here we have gradient x, the integral of gradient f, gradient xf and f vanishes, and so we don't have to consider about it. And here we have LFF, and here we have gamma FFF by taking inner product, and as I said, from the linear part, we can get this. And from the nonlinear part, we can get this. Oops. And this is a point we have used the property of a Banach-algebra, because roughly speaking, if f is small, gamma ff can be, behave like f square. And taking x norm means that we take Fourier norm, or sorry, capital X is here either L1k or L infinity k. So L1 or L infinity on the Fourier side. So if we take the Fourier transform of f squared, then it should be a convolution. And so we have estimate like this. This is a structure for the nonlinear part. Maybe we need some constant, although, well, anyway, that's another point here. So x can be either L1k or L infinity k, but for both cases, we can get this inequality. And using this inequality for both L1k and L infinity k and combine it, we have this estimate. So energy part and the dispersion part for I minus b is bounded by initial data. Usually this estimate does not close by itself, but L1, L infinity interplay is important for here. Now, how do we get PF part? Physically speaking, PF, velocity integral of PF represent the macroscopic quantities such as local density, bulk velocity, and temperature, and other macroscopic quantities such as tensor, stress tensor, or heat flux, etc., for higher order moment. So we may derive a fluid-like equation from the Boltzmann equation. This idea goes back to Hilbert in 1912. He did not use this idea for the energy estimate, of course. He invented this idea to consider the relation of Boltzmann equation and fluid equations, Navier-Stokes or Euler, or etc. It was rather recent that this idea was adopted to close the energy estimate. Now, PF can be written in this way. Here, A, B, C are functions of t and x. So A is function of t and x, and B and C are 2. But as a function of V, this comes, M is Maxwellian decays exponentially. So 1 multiplied with m half, V multiplied with m half, and V squared minus 3 multiplied with m half is a very good function. So from here, we want to study the behavior of A, B, and C. And by conservation laws, we can get these equations for the fluid part, ABC, and but they do not close because we have the information of I minus P here, where A and B are higher moments, like a third order or fourth order moment. To close the system, we also have to consider the time derivative, or the time derivative equation for this A and B. Then we can close the equation. It's lengthy, very lengthy to derive this equation. However, once derived, we can use usual energy estimate to have this lemma inequality. And we can see that this part, energy part and the dispersion part for I minus P was already bounded by the previous estimate, this one. And this part is also, again, nonlinear, so it will be bounded later. finally, if we want to consider the time weight and estimate, we have to consider something like this. By partial integral with respect to time, we lose -1 for the weight. And we decompose this integral into two parts. And k bigger than 1 part is easy because this symbol on the Fourier side behaves like a constant, so we can use the usual Young's inequality to get 1 plus t to sigma with a small constant and a big constant. But this can be bounded by the non-time weighted estimate. And for the k smaller than 1 part, this is more difficult because this may degenerate at k equals to 0. So by Young's inequality again, we can get, oops, sorry, this part for the large part, these terms for the large part, and in order that they should be integrable like this, we need a small epsilon. And here we have L infinity part, L infinity k part, but this is bounded by the previous step. So we can close the estimate. Sorry, I don't have to have time to explain this part, but I just say we can close the estimate by L1k and L infinity k. And here's a summary, but I do not have time to read them all, so allow me to skip this. And this is the end of my talk. Thank you very much. I am afraid, KH, I cannot hear you. Eh? Something wrong with it? But you are muted, so is it my problem? Oh, I now hear you. But you muted again.
Excuse me.
Ah.
Sorry.
No.
So I have a question about your main result, theorem 1.
Yes, wait a moment, please. Theorem 1. This one?
Yes. So in this setting, the domain omega is assumed to be the torus.
Yes.
So that you can get a good result.
Yes.
For example, the solution converges exponentially fast, and
yes.
And also the solution is positive. Oh,
yes, but this positivity can also hold for the R3 case, the whole space case. Probably this is a kind of type I just forgot. I just forgot to mention. Sorry.
So even if you consider in R3, you can get the positivity of the solution. Yes,
because Amixi also thought about that on the three-dimensional case, on R3. So we can, how to say, modify their argument for our case. Yes.
So could you give a brief explanation how to prove the positivity of the solution? So is it a difficult problem? No. The method is we decompose a solution F into two parts, that is F plus part and F minus part, and we derive energy estimate only for F minus part. And by using Gromwall inequality, well, there is a long calculation, but finally it goes to a Gromwall inequality, and we can conclude that F minus part should be measured 0. So it should be positive. Oh, I see. So that's why you can conclude that so the solution is positive even if the domain is R3.
Yes.
Okay. Thank you so much.
Thank you for your question.
Are there any questions or comments? So if not the case, let's thank speaker again.
Thank you.